In this online lecture, we will prove the following theorem. A Euclidean isometry that has exactly one fixed point is a rotation about that fixed point. Let us suppose that the fixed point of the isometry is the point O, and P is another point on the plane that is different from O. Suppose that capital T is the Euclidean isometry or transformation. Because T is an isometry, it preserves distances, and so P will be mapped onto a point which is at the same distance to O as P is. This means that T of P will be on this circle centered at O, and the radius is OP. We choose any point on this circle as long as it is not P for T of P, and call it P prime. Next, we take a point Q that is different from O, P, and P prime. Like T of P, T of Q will be on a circle centered at O, but the radius this time is OQ. To locate T of Q, we use the fact that capital T is a Euclidean isometry which preserves distances. So we measure the distance from P to Q. The distance between T of P and T of Q should be the same as this distance PQ. And so we draw a circle around P prime whose radius is PQ. T of Q will have to lie on this circle, and the circle that's centered at O and whose radius is OQ. Hence, there are two possibilities, Q prime and Q double prime. We will show by contradiction that Q prime cannot be T of Q. So let us suppose that Q prime is T of Q. We construct the bisector of angle QOQ prime. And here is the angle bisector. We take a point B on this angle bisector. Like we did with T of P and T of Q, to find T of B, we construct a circle centered at O and whose radius is OB. T of B should be the same distance to Q prime, which we assume to be T of Q, as B is to Q. And so we draw a circle around Q prime with radius BQ. So T of B is one of the intersections between this orange circle and this black circle that passes through B, so that B is still a candidate for T of B. Using P this time as a reference point, T of B should be the same distance to T of P as B is to P, and so we construct a circle centered at P prime with radius BP. So T of B should be on these three circles, and B happens to be the only common point among the three circles. So T of B is equal to B. But that also means that B is a fixed point of the transformation, which contradicts what is given, that capital O is the only fixed point of the transformation. Therefore, Q prime cannot be T of Q, but Q double prime is. Now that we've settled that T of Q is Q double prime, we have to show that T is a rotation. To prove this, we will show that angle QOQ double prime is congruent to angle POP prime. We designate angle QOP as angle A. Call angle POQ double prime as angle B. And let angle P prime OQ double prime be angle C. So angle QOQ double prime is equal to A plus B. Angle POP prime is equal to B plus C. Now angles A and C are congruent because capital T, being a Euclidean isometry, preserves angles. Also, one can show this to be true because triangles POQ and P prime OQ double prime are congruent by SSS congruence. And so angles A and C are congruent by CP-CTC, being corresponding parts of congruent triangles. Hence, A plus B is congruent to B plus C. And angle QOQ double prime, which is A plus B, is congruent to angle POP prime, which is B plus C. Therefore, T is a rotation around the point O.